Okay, now remember to follow the format on this stuff, right? So your name, date, homework number, problem statement, sketch, box in your answers, that sort of thing. All right, so what do we got? Did I assigned 131, I think. Okay, and that looks like this, I believe. Yeah. All right, so one thing that I'd mention is, these things aren't always identical, but usually I try and model how to do things in class so that you got some idea how to approach problems. So, and this is one very much that way. I mean, if you look at the stuff that we did in class, we did one very much like this. It was that problem, we started off doing it graphically, and then we shifted over to doing it with trigonometry, okay? So if you're trying to figure out how to do something and you're not quite sure, the first thing to do is to look at what we did in class and try and find a template for how to approach a problem. And this one has one, okay? Okay, so what you're going to have here on this one is you're just going to want to take these vectors and break them into x and y components. That's basically the approach on this. So I think I did F1 here for you. Okay, so I'm going to break each one of these vectors into x and y components. Now, you could do this in different ways. So what you would want to do here would be to figure out the dimensions. Now this one, for instance, has a 24-degree angle there that's labeled, but you could also use 156 here as well, okay? Like so, okay? So right in there, that's 156 degrees. Lost my pen here for the moment, so I'm just trying to do that with a mouse, but that's 156 degrees, okay? So you could use either angle. And then what you do is you just break them up into x and y components. So you could either use the 156, which is a counterclockwise angle from the positive x-axis. If you do that, you don't need to worry about the sign. You would just go 680 cosine 156, which would be the x component, and then the sine of 156 would get you the y component. That's one way to do it. Now, the other way to do it is to use the 24 degrees, which is given, and then use the fact you can break that thing into a right triangle just by using that 24-degree angle and the 680 magnitude. So you've got a right triangle right there. The 24 degrees is right in there. So what you could do then is use the sine, or excuse me, the cosine. And using the cosine, you'll get the adjacent side. And then use the sine to get the opposite side, okay? So you could do that. Now, if you do it using the 24-degree angle, you do need to include the direction on what you're doing here. So the 680 sine 24, which is the y component there, the opposite side, that's positive because it's going up. And then the 680 cosine 24 is a negative because it's going to the left. Okay? So you could do these either way, whichever way suits you, I think is fine. And however you do it, you want to come out with an x and a y, all right? Negative 621 and 277, basically. Okay. So, you got any questions on that? Doing all right? And then I like to organize these things so that, you know, I've mentioned this before, and, you know, so that I got all the x's in a column, I'll just add them up, and I got all the y's in a column, and I'll just add those up, and then I'll get my resultant down below. Okay? So you'll do the same thing for F2 and just add up the x's and y's. All right? All right, so you should get some of fx is about negative 158, and some of fy is about 828. Okay. And then once you've got that, then you could go ahead and solve for the resultant force. Now what you get for the resultant is you take the square root of the sum of the squares. So there's sum of f resultant there is a vector, negative 158i plus 828j. Take the sum of the squares, you get 843.2, and then you could do the arctan and figure out the angle, the inverse tangent, 100.8 degrees. So we all right with that? We got any questions with that bit? Yeah.
Can we use, instead of like 100.8, like 10.8 west of north, something like that?
Well, let's see. If you're going to do anything like that, label the angle with a sketch. Because what that does for me is it removes all ambiguity, you know, of standards and where you're coming from and all that. So just put a sketch, put the arrow going the right way, and label it somehow from an identifiable axis. And however you want to do it, then it's fine because it's, you know, it's unambiguous. Okay. Yeah. Okay. Other questions? Doing all right? All right. So that's the drill on that. Okay. That's how you do that. Okay, we got another one that's an awful lot like this. It's similar, 122. Now this is the one that you did graphically that you've already turned in. So it's the same sort of thing. You just break up those three vectors into x and y components, and then you you know, get them on and add up the x's and add up the y's. Same thing. And so, you know, we just want to be able to use some trig here and do this sort of thing with these vectors. I mean, that's part of what we do in here. Okay. So we got any questions on the next one? Doing all right? Okay. We're good? All right. All right. Now 141, we start getting into 3D stuff. So do we got questions on this one? We could look at the basics of it, but I'll just see if anybody's got any questions on this one. 141. Okay, we got F1 there. So what's F1 doing? F1, you can see the angles there for F1, and what you want to do here is just look at where the dimension line originates, where it starts, and where it ends, okay? So there's the angle with the z-axis for F1. Here's the angle with the x-axis. And here's the angle with the y-axis, okay? So just look at where those little dimensioned arcs start and finish, and that's telling you what axis they reference to. So what you're going to do with that, you're going to take the cosine of each of the angles times their appropriate axis, ij or k, and then multiply that by the magnitude of 70. And that's how you get F1. I mean, there ain't much to it, okay? So 70 cosine 72.36, cosine 120.34, and cosine 36.09. You can then work through that and get F1. Okay? Now you can do the same thing with F2. All right, and you'll get down to that answer that I'm showing. Now with F2, the one thing I would caution you with on that one is you're given this 57-degree angle right there. Now notice that is not with the positive z-axis, it's with the negative z-axis. So you're going to have to account for that in some fashion, okay? So you can't just go cosine 57 times 50 for that. You have to adjust for the fact that's negative. And there's different ways to do it. The one thing I'd caution you on is, just remember your trig here. The negative of cosine 57 is not the same thing as the cosine of negative 57. They're different things, okay? Just basic trig there and how that works. But you'll just have to account for that. Okay. Okay, so you'll get F1 and F2. Any questions on those? Add up the components. Square root of sum of the squares will get you the resultant. Okay. Good with that? Okay. So that's 141. All right. All right, now 143 is a little bit trickier there. It's the same idea. F2, you'll just do the regular business with that. You've got the three angles, so you'll take 3,000 times the cosine of each of the three angles. So that's what you'll do with F2. F1 is one of those double projections, okay? So the tip-off to this for F1 is you got a few things. First off, you got this vector going on up here. You're dropping it straight down like that. So that's in the y direction. And look where you end up with that. You end up on a point that is extended out from the x-axis in the y direction. Okay, so this point here is in the xy plane. Okay. So you have to be able to read those dashed dimensions in a certain way that you can figure these problems out. Is there any question about that point being in the xy plane? And that, okay.
Is that because it's parallel with the y-axis?
Yes, right. That line that I've kind of underlined in yellow extends off from the x-axis in the y direction. So its endpoint then is in the xy plane. You kind of got an x component to that line, or that dimension I should say, then a y component. So that's where that endpoint is. Okay? So that, that's the reasoning behind that, and you just want to recognize this, So that point right there is in the xy plane, right in there, okay? All right. So what you're going to want to do about that is do a double projection. So when I think about this, what I think about is a two-step process to get that line projected over to where I want it to be, because what I want to find on this are the x and y components. Okay? So what's going to have to happen here is, first, to get into the xy plane, I'll use the cosine of that 72-degree angle. That'll get me down there, and that gets me to that dashed line that goes off on a diagonal that's marked 41 degrees. Once I've got it there, then I have to swing it a second time to get it onto the x-axis. So I'm going to have to apply two cosines to that. I can't just add the 72 and the 41 together because they're not coplanar. It doesn't mean anything to add them together. But I do the cosine of 72, then the cosine of 41. That'll get me over to the x-axis. You okay with that stuff there? Okay.
What do you do then for the
Okay, let's kind of have a look here. Let's see. Okay, so for alpha there, you're kind of combining cosine 72 and cosine 41. Now for beta, what's going on is, see, when you do that cosine 72, you're down in the xy plane. You just have to find the angle from there to the y-axis is what you need to do. So what you need to do is to figure out, once you've swung that F1 vector down into the xy plane, what is it going to take to get it projected over here to the y-axis over there? And actually, it'll end up being a negative on it because it's going to go in the negative y direction. Okay? So you'll have to figure that out. All right? And you'll take that result and multiply that by 2,000. And then the last thing you'll need to do is figure out this angle right here, which is gamma. Now there is one gamma angle right there. And what you're doing there is you're taking that projection that comes out of the xy plane and you're figuring out how much further you have to tip it up to make it normal to the xy plane. So think of doing whatever, raising a flagpole or something, and you're tipping it up. You got a pulley on a rope on the top, and you're pulley a system of some type. What more is it going to take to get that thing vertical? That's the idea. Okay. How much more do you got to tip it up to make it vertical? Okay. All right. So those are the three things that go into that unit vector. So cosine 72, cosine 41, that gets you 0.233. That's the first little bit that you do with this. And then you also have, you got to work with it again to get it on the y-axis. There's your second unit vector component. And then you got to get it on the z-axis. There's the third. And then you multiply all those by 2,000. When you're all done with this stuff, that should be your final force vector right there. Okay. Questions on it? Doing all right? So that's the homework that's coming due tomorrow, okay? I've got that link up in Moodle for those of you that are online.
President?
Yeah.
So for gamma again, sorry, on F1, it looks like with 0.951, given as what that cosine of whatever the angle is, the angle is about 18, which would be 72 plus 18 is 90.
Okay.
The 72 I thought was extending further past the y-axis. It wasn't going to the y-axis.
What the 72 degrees is that's an angle up from the XY plane.
So it is going to the y-axis.
No, the 72 does not go to the y-axis. It goes to the XY plane. It's the shortest angle to the XY plane.
But yet the angle gamma is still 18 degrees.
Okay. 72. How much more to make it normal?
Yeah, exactly. If 72 isn't going to, so the whole angle should be 90 degrees, but 72 is extending past the y-axis. So it should be 72 plus gamma should be larger than 90 degrees.
No, I don't agree with that because the z-axis, the only criteria on the z-axis is that it's normal to the xy plane. I mean, it is also makes a right angle with the y-axis, which is, I think, what you're focusing on, but it makes a right angle with the x-axis. It makes a right angle with any line in the xy plane. So it isn't like there's something special about the y-axis. It's the 90-degree angle simply with the xy plane. Other Questions on that? Doing all right? Yeah, just to kind of illustrate that, I mean, here's X and Y. And here's that vector. It doesn't have to, it has nothing to do with the y-axis. It's just this angle in here is 72. You just pull up further. See, this makes a right angle with any line in the XY plane. There's nothing special about the y-axis. It's the whole plane. So that's the deal. Doing okay with that? Other questions? Okay. All right, then what you're going to do, you're going to add everything up and find the resultant, add up the X and Y components. Once you have that, you can find the magnitude of the resultant. You can find the unit vector for the resultant. And I think part of this question was to find the, so there you go. Okay, so that'll be the 4 of them. All right, so we'll kind of keep going here on this stuff we got into yesterday. And what we were doing yesterday was projections. So what a projection is taking a force and finding the component of the force that acts on a given line. So in 2D, this is pretty straightforward in that if you've got a force at an angle with a line, you just use cosine of the angle times the force, and that will get you the amount of the force that acts on the given line, okay? So that'd be F cosine theta. Now in 3D, it gets trickier because you can't find theta quite as easily as you often can in 2D. So in 3D, we need a little bit of a mathematical tool that we can use to accomplish that, all right? And there's a nice tool that was developed in mathematics. It's called a dot product. And I'm not sure which page we're on here. So where are we at? 200? Okay, thank you. Okay, we're on 200. Okay. Now, a dot product is a scalar. If you take two vectors and dot them, what you get is a scalar that equals the magnitude of one vector times the magnitude of the other times the cosine of the angle in between. All right. Now that cosine function is kind of key here because cosine of 0 is 1 and cosine of 90 is 0. So if you know that, you can find the dot product between any two unit vectors. If you dot like unit vectors together, I dot I, j dot j, and k dot k, it equals 1. Okay? Now notice you don't get a vector out when you do a dot product, you get a number, a magnitude. All right. Now when you dot unlike unit vectors together, what you get then is you get 0. Okay. So if we take two vectors A and B and dot them together, what's going to happen is most of that stuff's going to cancel out, all right? Anytime you dot the two unlike vectors together, it zeroes out. Now what we're doing here, we're using the distributive law, and we're dotting every component of A with every component of B. That's what we're up to. So if I dot A with B, most of it cancels out, and what I'm left with is AX, BX, I dot I, which goes to 1. AX, AY, BY times J dot J, and J dot J goes to 1. And AZ, BZ times K dot K, and K dot K goes to 1. So what I end up with is just a sum of AX, BX plus AY, BY plus AZ, BZ. If I add those together, I get the dot product. And if I have the dot product, what I've got is the magnitude of A times the magnitude of B times the cosine of the angle in between them. All right? So that's about it. All right, now let's figure out how to use this dot product to find a projection. So the first thing that we want to do is just, we got a little example there on the bottom of the page. If I've got A is 3i minus 4j plus 2k, and B is 2i plus 5j minus 6k, I show how to do a dot product. Just multiply the like components together and add the products. And that's really about all there is to it. Okay. Remember, you do not get a vector out when you do a dot product. You get a scalar, and in this case, it's negative 26. All right, now we have a couple uses for this thing in engineering. You can use this to find the angle between two 3D vectors, which is handy. You can solve that expression for cosine theta and then solve for theta. That's one thing you can do with it. You can also use it a little bit more directly to find the projection of a force onto a line. And in that lower right-hand corner, it's pretty small there, but I kind of squeezed that in where I've got a force acting on a little strut there. The strut goes from A to B. The force goes from B to C. So let's figure out how I would find the projection of FBC onto line AB. Okay. All right, now the first thing to understand here is that the projection of FBC onto line Well, we'll think about that. We might have to have a little chat there. But anyway, here we go. So what we're looking for here is FBC. We want to start with that. Okay, that's what we want. And then what we want to do is multiply that times the cosine of that angle. Okay? Like so. That's what we want. Okay, that's what FBC parallel to AB is. So we can't just dot FBC and then the full line BA. We can't do that. We've got to work with them a little bit more than that. But let's see how we can take a dot product and the information we've got that I've circled up there and get it to this, because that's what that projection would be. FBC times the cosine of the angle between. So let's have a look. All right, so what we got here is the projection of FBC onto line AB is FBC times cosine theta. Now what that equals is FBC times 1 times cosine theta. Those are equal things. Now I know that A dot B is similar to this. It's AB times cosine theta. Okay, so we notice we got some things that are pretty similar. We could use A as FBC. We got cosine theta and cosine theta. That's all good. The one little problem we got here is B. Okay, because what B would line up with would be the number 1 right there. So we can't use the full vector B, which in this case would be the length of that strut that we're projecting onto. All right. What we have to use instead is a unit vector for the strut. That has a length of 1, a magnitude of 1, so that will turn into this middle term, okay? So if we want to find the projection of a force onto a line, we take the full force vector and we dot it with the unit direction vector of the line. It's got to be the unit vector of the line because I don't want the magnitude of the line to enter into this. The length of the line, it doesn't make any difference. I just want to know how much force is going through that line. I don't care if the line is 2 meters long or 10 meters long or whatever. It doesn't make any difference. I'm just trying to find how much of the force is projected along it, okay? So I need a unit vector for the line. Not the full vector, but the unit vector, okay? So that's the operation for finding a projection. All right, so it's going to be the force vector dotted with the unit direction vector. So are we okay with that? Okay. Now the other thing we could do if we want to find the angle is we could take A dotted with B is AB cosine theta. All you got to do is kind of take that thing apart and solve it for theta. I just solved it for cosine theta. So if you want to find the angle between two vectors, you can dot the vectors together and divide by the product of their magnitudes. Or you can realize that A over A and B over B are vector unit A and unit B. So you could solve for cosine theta just as the dot product of the two unit vectors too. Okay? So this is a way you can find the angle between two lines if you like. So the projection is a force vector dotted with a unit direction vector. The angle is solved by using cosine theta is the unit vector for the one line dotted with the unit vector for the other. Okay. So that's the two things that engineers might do with this dot product. And I honestly don't know why mathematicians came up with this thing, what's so special about it, but it's very helpful for us doing our 3D stuff. Have you guys gotten to this in 254 yet, this dot product?
Yep.
What, do you do anything else with it? I mean, do you find the angle between two lines? What else do you do with it? Anything else come to mind other than what we're doing with it? Nothing yet. Okay. Yeah, I don't know. I can't think of anything, but I don't know. So I don't know why the heck they, someone just came up with this. I don't know what's so kind of magic about it, but
Well,
somebody
it
did.
was for this sort of situation.
Yeah. Yeah, maybe that's probably enough,
All mathematics, pretty much all mathematics is driven by, what science or engineering needs.
Well, I don't know, always, because mathematicians will go off into theory land, they do stuff that isn't directly applicable, and then, 100 years later, someone comes by and goes, oh yeah, this will work to model such and such. So I don't know, it's like there's a thing on that Einstein's relativity theory. We put a little thing in his treatise that thanks some mathematician for coming up with something like 10 years before, because he used it to describe some of his theories. So, it is kind of that fundamental difference between mathematicians and engineers. Mathematicians are just interested more in the relationships, and then engineers use them more. But anyway, so that might be a good question if although I don't know if you get much of an answer, but for one of your math teachers. Okay, so let's have a look at 210. Let's see if we can find the projection of a force onto a line, okay? Now, let's start by saying, well, why do we want to know this, all right? What's the purpose of this? Why are we up to this? Why do we care, all right? And here's the answer. You can't design every possible you can't come up with a table or something that tells you how to design a strut or something like that for every possible force at every possible angle. It's infinite. There's just too much you would have to do. That's one thing. Now another thing that goes on here is materials have basic types of stresses and forces that are applied. One is what we call axial. And what that does is it takes the molecular bonds in the material and it stretches them or compresses them. Think of if y'all had a bit of chemistry, you got little atoms, little balls kind of floating around, and they get stuck together with bonds. And think of the bonds as being like springs, okay? So one basic type of stress that a material undergoes is when those springs are pushed and pulled on directly, okay? And we call that an axial force. Compression pushes on a member, tension pulls the member. So you can look at a material and say its tensile strength is such and such, its compressive strength is such and such, okay? So that's one basic way we analyze materials: direct push, direct pull. So if you look at the concrete piers, if you've got that kind of foundation under your porch or something, they're being compressed. You're pushing on them, okay? If you look at the, I don't know, it's in tension, a lot of things are, but you know, if you look at a slingshot, if you're pulling on that rubber band, that's under tension, is what's happening there, okay? And those are very basic types of stress. So we analyze materials in that way for tension and compression, axial, which we call axial stress or axial force. Now the other basic type of stress and force we look at is called shear. Now what shear does is take one plane of atoms and slide it across the other, okay? It's perpendicular or normal to the axial, to the compression or tension. And that's another way we analyze materials. So those are the two basic ways that we analyze materials. And if you look at material strength tables, they'll give you the strength in tension, in compression, and in shear, okay? That's how we look at things. So rather than coming up with tables and tables and tables of forces at all these possible different angles, what we do is we take those angled forces and we break them up into an axial force, either tension or compression, and a shear force, which is normal to the axial force. And then we got a more kind of organized, concise way of analyzing things. Those are also the more kind of basic types of forces that are applied to materials. A stretching or compressing action is very different as it pulls and pushes in on those bonds as a shearing action is, okay? Okay, so compression and tension are about stretching those springy bonds in and out, like an accordion kind of, like that. Shear is about taking one plane of atoms and making it slip across the other, okay? So if you ever seen a picture of like an avalanche, when it first starts, that's usually a shear failure. One layer of snow slides across the other. Landslides are that way. There's a lot of different examples. Shears are called shears because that's what they do. They, you know, one side of the scissors holds the paper, the other cuts it clean perpendicularly across, okay? That's why they call them shears, okay? All right? So that's why we do this. So we can take these angled forces and break them up into things that we can then start to analyze the material for, right? These two basic things. Okay, so we'll use these words. So tension, compression, and shear, and also axial force, which is tension or compression, one or the other. Tension's positive because it pulls out, and compression's negative because it pushes in. Okay? So that's why we get into this. That's why we would want to do this. Y'all okay with that? Okay. Good. So what we're going to do then is we're going to take that force there and we're going to break it up into, it turns out, we'll look at both tension and, or actually that's compression and shear on this thing is what we'll do. Okay? And this will just be that basic process of accomplishing that. Right there, okay? So, that's probably, let's see. So there we are, okay? So we got 300 newtons. We got the coordinates on there, and then we're going to figure out the angle. We're going to figure out the projection of FBC onto line AB, which is the compressive force in AB caused by FBC. But we don't have enough time to do that today, so I think we'll do that tomorrow. So that's probably about as far as we'll go on this. We good? All right. Call it good?